Quiz is going to be on Tuesday. That'll be like a reading quiz, just like we had before. And that quiz will cover the first part of Chapter 2. Let's do up to page 48. Pages 34 through 48, right up to where it says applications to the human body. So these chapters are sort of roughly divided into physics and then the human applications. So we'll just get the physics portion in this first quiz. And then we'll have another quiz. Huh? You can read the whole chapter if you want. But the quiz is on up to page 48. Is that clear? This is the quiz on Tuesday, up to page 48. And then on Thursday, there'll be the test. Dun, dun, dun. No, it'll be similar to the quiz that we had before, right? Those types of questions. They'll be from the book, largely. Although remember, there is that additional material about the dimensional analysis, units. What else was there? Those first things that we went over. All right, I think that was largely it. Units and dimensional analysis. Yeah, that was it. And so that'll also be on that test. All right? Probably the way it'll work on that Thursday is we'll come in and have about 30 minutes of class time. I know that's not real great for y'all, but we'll probably have about 30 minutes of class time and then spend about 50 minutes on the test. Just can't really, I'm sorry. Chapter 1 only, right. So the test will only be on Chapter 1. But there's a lot of material in Chapter 1, a lot of different things. Do you have any questions before we get started about Chapter 1 or 2? We had just started on Chapter 2. No? All right. Well, so on Tuesday when you come in, the last 20 minutes or so of class, we'll take that little reading quiz. Oh, on the test, by the way, you'll need to bring a Scantron form, okay? And I don't think you'll need a calculator. Y'all have calculators? Yeah. We'll see. I haven't written it yet, so I don't know. But I'll probably make the numbers so simple that you won't need calculators. Right? Y'all okay with that? Okay. Trust me on it. Okay, so let's see. We were talking about pressure. Remember, we had a lot of different units: the Pascal, the British system, the PSI, which is pounds per square inch, like in your tire. And then we said these measurements represented what? The millimeters of mercury, inches of mercury, or centimeters of water. What did those measurements represent? Right, the height of a column. Who said that? Was that you? Yeah. So yeah, they represent the height of a column, and we'll see today where that comes from, how that height comes about. Let me go ahead and replace my battery here before it dies on me. We'll also look at atmospheres. Atmospheres are also due to the height of a column, but in this case, it's going to be the height of a column of air that's over your head. Would anybody like this battery? There's probably enough juice in it, like if you want to stick it on your tongue, it'll... Okay, I've never put my tongue on it, if y'all want it. It's clean. All right. Okay, then we said there are three possible sources of pressure in a fluid. The weight of the fluid, and like I said, that comes about with atmospheric pressure, which we'll talk about later. That if I'm walking around with this column of air on top of my head, and that column of air goes all the way to space. And that's a pretty heavy column of air, and that causes a really great pressure at just 1 atmosphere. Also, external force applied to the fluid, like in a syringe, and then internal forces due to molecular interaction. Yeah, and the first thing we did, sort of did this loose derivation. You're not responsible for the derivation, but define the pressure at a certain depth is equal to the density of the fluid, rho, the acceleration due to gravity, 10, and the height or the depth of the liquid. Okay, I want to show you a little video. This is just, as I said, if we're on the planet Earth, you're here, this is the planet Earth, there is this column of air that goes all the way up to space. And it has a pretty immense weight. And it pushes down when we're on the Earth. It pushes on us in all directions and causes a pretty large force. In fact, 1 atmosphere is equal to 100,000 newtons per square meter. We said this on the first day when we went into this chapter. So that column of air is producing a pressure of 100,000 newtons per square meter. So if I were to put out a square meter, then I would have 100,000 newtons of force acting on that square meter. But that doesn't really make any sense, right? Because y'all are all sitting in your chairs, and honestly, if I came in, if I punched you with 100,000 newtons of force, which I wouldn't because I don't touch students in general, but if I did punch you with 100,000 newtons of force, that would hurt or not hurt? It would hurt a lot, right? A person is like 700 newtons, so that would be an immense force. So why is it that we're not just laid out on the floor because of this 100,000 newtons of force? Is it because it doesn't really exist, that atmospheric pressure? Or what? What's that? Okay, that's true that your body, because of Newton's third law, she said that your body pushes back with an equal force, and that is true, but not really. That's not the answer to my question, but it's a true statement. It's because you have this force acting on all points in your body, and so I have a force pushing this way, but then I have an opposite force pushing the opposite way. And your body is basically incompressible because it's largely water. So you don't feel it really because, we grow up in it. But you can demonstrate it. This little video just shows a demonstration of that. You can try this at home, or like I said, if you're out walking around with your meter stick, because you wanted to show everybody that center of mass thing that we did, you can also do this with a meter stick and a very flat sheet of newspaper. So let's watch this. It's just a couple minutes. I'll stop at 45. P is smaller than P naught. That was B. Let me show you the two scenarios right next to one another. I think it might make a little more sense to you. If I have a manometer here with a fluid inside of it, and the fluid looks like this, where this is my P naught. I have a big P naught in this case and a small P in this case because the pressure due to the atmosphere is bigger than P, and so it's able to push this column of liquid down further into the pipe. Whereas if it were the other way around, it would look like this. Now in this case, P naught is bigger than P. If it were the other way around, it would look like this. In this case, my pressure P is big and P naught is small. So in this case, P naught is less than P. So if you were going to calculate these, you would say that the pressure equals P naught plus or minus rho GH. Minus, because it's smaller than P naught. And over here, I would say P is equal to P naught plus rho GH. You're not going to have to use those formulae necessarily, but you do need to know how to interpret these, that I can tell how the pressure is. Is it bigger or smaller than the standard pressure, where the standard is our P naught, which in this case is the atmospheric pressure. Do you have a question, Destiny? No. All right, now let me show you that's a manometer. A more common thing to use is a barometer. And a barometer is just like a manometer. Yeah. It's Ashley? Macy? Casey? Kaylee. Okay. P naught. Yeah, I'm sorry. Whenever I write a 0 like that, it's like I say P and then naught. Like I shall not do that. Yeah, not. I'm sorry. Kaylee? Okay. But it's just it's a term meaning like a standard, or sometimes we use it for initial conditions. All right, now a barometer is very similar. And we more commonly see barometers, like for example, a barometer we use to measure atmospheric pressure. So a barometer looks like this. I have some material, mercury, water, alcohol, whatever, like, like rubbing alcohol. And there's some pressure that's pushing down out here. I want to know what that pressure is. And inside this column, I have a vacuum. That means this is my P naught inside. And since it's a vacuum, what's the pressure? There is no pressure, right? If there's no material, then there's no pressure. So since I have a vacuum, there's zero pressure. And I measure the height of this column, h. And the same formula still applies. That is that P equals P naught plus rho GH. But in this case, since P naught is equal to 0, then the pressure is just equal to rho times G times H. Now remember, this expression was the expression to find the pressure at a certain depth, right? And so we use that idea here, that if I want to know the pressure pushing down on here, I just measure the height of this column, and then that tells me what is the pressure pushing down to push this column up. All right? A drinking straw works in a very similar fashion. So again, this is something you can tell your friends. If you have can I go to the next page? A drinking straw works a lot like this. When you're actually drinking liquid out of a straw, it looks like this. This is my beverage. I have a straw that goes down into it. It's filled with some liquid. And what you do, let's see if I can draw, we'll just say that's a mouth, okay? Hey, that's pretty good, actually. So that's somebody on this very large straw trying to get drink out of this very large cup. Um, so what you do basically is you decrease the pressure here. You decrease the pressure. And this is similar in our barometer. You're decreasing P naught so that the pressure here will push that liquid up into the straw. All right? Now let's imagine that I have water in a barometer. And in fact, the first barometers used water. We're going to come back to the straw. This is a point. If I have water in a barometer, the barometer looks like this. I have water inside of it. There's a pressure that's pushing down. That pressure is equal to 1 atmosphere, or 100,000 newtons per square meter, just like the pressure that we saw pushing on the newspaper. You can calculate the column of this liquid that's going to come up into the barometer. If I say P is equal to rho times G times H, I'm just going to do this quick calculation. I know that my pressure is 100,000. That's the pressure due to an atmosphere. That's in newtons per square meter. Right, that's 1 atmosphere of pressure at sea level is 100,000 newtons per square meter. Do I know the density of water right off the top of your head? Okay, well, it's 1 gram per cubic centimeter. But in this case, I want to use SI units, and it's going to be 1,000 kilograms per cubic meter. That's the density of water. G is 10 meters per second squared, and I want to solve for H. So that's 100,000 divided by 10,000. So H is 10 meters. So in a barometer, where P naught is equal to 0 because I have a vacuum there, the column of this liquid is going to be how tall? How tall? It's going to be 10 meters, right? Because I have the atmospheric pressure pushing down and pushing up into this this straw-like thing. I have a vacuum here, and so it's going to push it up to 10 meters. All right? Now over here, with the straw, this is like an imperfect barometer. Because if you create a vacuum here, that means you'll have the full force of the atmosphere pushing down onto the liquid and pushing it up into the straw. What is the maximum height, do you think, that you can have a straw and actually pull up liquid into that straw? Do you think that maximum height is A, less than 10 meters? This is the maximum length or maximum height of a straw where it'll actually work. Is it equal to 10 meters or is it greater than 10 meters? Understand the question that I'm asking? I have a straw. I want to pull up liquid into it. What is the maximum height that that straw can be? Like if I wanted a 50-foot straw, would that work? Let's try it. I want to see what you think. What is the maximum height of a straw? Is it less than 10 meters, equal to 10 meters, or greater than 10 meters? I'll stop at 35. 35. Okay. I have a little video I want to show you about this. The answer is C. You know, I have to, in order to take liquid up into the straw, think about this when you're at lunch today, if you use a straw, and I have to create a low pressure area right here. What's the lowest pressure that I can create in my straw? That's the question. What's the lowest pressure that I can create in my straw? It's supposed to be obvious. What is it? Zero, right. Because zero would be a vacuum. I can't create less than a vacuum. Like if I take all the air out of it, I can't take out more air and make less pressure. So my lowest pressure that I can create here with my mouth, in an ideal situation, to create a perfect vacuum with your mouth is basically impossible. But if I were, I don't know, really good at drinking through a straw, maybe I could create a perfect vacuum there, all right? And if that was the case, it would be like a barometer. Okay, I'd have a barometer with a column of liquid. This would be pushing down into it, pushing up into the straw, and I would find that the height of that column of liquid would be 10 meters. But that's under the assumption that I've created a perfect vacuum in the top of the straw. I have a little video here. This is from the Veritasium channel. It's about 6 or 7 minutes, but I think it's very interesting. He's trying to create the longest straw, the longest possible straw, which is going to be about 10 meters, or roughly how many feet is that? 10 meters, about 30 feet, right? So let's watch this. Let me show you. Let me draw a picture here. I guess this is difficult. This is difficult to This is a difficult concept, huh? All right. All right, look. There is a lot of thinking. All right. So here's my liquid. And when you're not drinking anything, you have atmospheric pressure pushing here, PA. And then I also have atmospheric pressure pushing there, PA. And that pressure is transferred up to here, and so it pushes up into the straw. But when you put your mouth on the straw, you decrease the pressure inside the straw. All right, so now I have a high pressure on this end and a low pressure on this end. And whenever I have a pressure differential, we call it a difference in pressure, it's going to move from high to low pressure. So where I have a high pressure pushing down on this, it's going to push that liquid up into the straw. Yeah, it's not osmosis, but yeah, it's similar that you have this. Is that osmosis, high to low? Okay, yeah. I guess it is similar then. Does that help? Okay. Yep, try. Go out for lunch and get a straw. And maybe it helps. Okay, let's try the next question. They discuss this in your book some, but not a whole lot. Okay. Thermometers, they often use mercury or alcohol. And thermometers, the reason they use alcohol is just because uh, mercury is toxic, right? Like if you get it on, if you ingest it, it's dangerous, it's toxic. So they use alcohol often in thermometers, but barometers never use alcohol. Why is that? Why would a barometer never use alcohol? Which of these reasons? Why do we use mercury in a barometer? All right, I'll stop at 105. All right, very good. D. Mercury is a lot more dense because if we use something like water or alcohol, which is even less dense than water, our column would be how tall? More than this? It would be how tall? If we used water in a barometer, how tall would the column be? More? More? How tall would it be? How tall? 10 meters, right. It would be 30 feet tall. In fact, the first barometer, they used wine, and it was about 30 feet tall. So, all right. Okay, we'll come back to this. We're going to get into fluid flow later in this chapter. All right. So let's look at pressure due to an external force. As I said, he talks about all these barometers and the drinking through a straw and pressure and what have you in the chapter. So take a look at that. We still have questions. We can address it next time, but so take some time to sort of dwell on it. All right. With pressure due to an external force, we're going to introduce the idea of Pascal's principle. Pascal's principle is pretty simple, but it has a lot of different applications. Um, Pascal's principle says that when pressure is applied, to fluid in a closed container, and actually an incompressible fluid, I'll just put this in parentheses, an incompressible fluid in a closed container, the pressure is felt throughout the container. The same pressure is felt throughout the container. All right, so if I have a piston here, it's filled with some liquid, and then I have this is my piston, I can apply a force per unit area. So I apply a force here, it's applied over a certain area, and so the pressure there is equal to force per unit area. And let's say I apply, I don't know, 100 pascals or 100 newtons per square meter of pressure. That means that all throughout this fluid, I'm going to feel 100 newtons per square meter of pressure. That means that on the side of the container, I'm going to feel 100 newtons per square meter of pressure. All throughout the liquid and all throughout the fluid, I'm going to feel this 100 newtons per square meter. And also on the sides of the container, I'm going to feel this 100 newtons per square meter. All right? What does it mean, or why is it relevant that it's incompressible? First of all, what does it mean to be incompressible? It's unable to be what? Compressed. Right. So what are some things that are not compressible among fluids? Remember, fluids are things that flow. What is a fluid that's not, that is compressible? What's a fluid that's compressible? All gases. All gases are compressible. That if you take a gas and you collapse it down, it's compressible. We'll talk about this when we talk about fluid flow. But let me go ahead and write that here. So gases are compressible. Just because if you change the shape of their container, you'll change the shape of the gas. They fill the size of the container. What are incompressible? Hmm? Okay, mercury, all liquids basically. All liquids basically are incompressible. So liquids are incompressible. All right. So water, for example, is incompressible, which is a good thing, right? Because we have these large pressures pushing on us, but fortunately we're not that compressible, so we don't collapse us like that little water bottle that went down. Okay? So liquids are incompressible. So this applies only for liquids. Do you know what kind of systems, mechanical systems, this idea is relevant in? Hydraulic systems, right. So hydraulic systems make use of Pascal's principle. I want to show you a simple hydraulic system. I think it's useful for you to know how this works, though it's not discussed in your book. So you might want to put a star next to it in your notes. This is not in the book. So Pascal's principle is used in hydraulic systems. And hydraulic systems are used in all sorts of scenarios. From, auto shops where you're trying to lift a car to doors where they have the pistons on them, the things where you want to lift heavy things. Well, let's just consider an auto lift. An auto lift looks like this. I have a pipe that's filled with liquid, a hydraulic fluid, but it could be filled with anything. It could be filled with water or any liquid. Why don't they use water in hydraulic systems, by the way? It's really cheap. Why not use water? Because it would do what to the system? It would rust, right. Yeah, so it's rusting. So that's the primary reason. So what Pascal's principle says is if I put in a pressure here, P1, I'm going to get that same pressure out here, P2. So Pascal's principle says that P1 is equal to P2. Or I can call it instead, it might help you to think of it as the input pressure is equal to the output pressure. Pascal's principle says that if I put in a pressure here, I'm going to feel that pressure all throughout this incompressible fluid until I get the same pressure out over here. And these are movable pistons, so they move when I put a pressure on them. Now, if we remember, our pressure is force over area. All right? So given this is a Fn bigger than F out is Fn equal to F out, or is Fn less than F out? Try that on your own, or you can ask your friends too. Is the force is a force that I put in over here bigger, smaller, or equal to the force that I the force that I get out? Is my input force my input force bigger, equal, or smaller than the force that I get out? The pressures are the same, but notice how the areas are different. The way that I've drawn it, the area on the left-hand side is much smaller than the area on the right-hand side. All right, I'll stop at 105, 105. Okay, let's look at this mathematically just a little bit. Let's say that I put in, I don't know, 100 newtons per square meter. And I'm going to get out a pressure that's equal to 100 newtons per square meter. That's true. That's what Pascal's principle says. That if I put in a pressure on one point, I'm going to get the same pressure out. Well, let's say that the area over here is 1 square meter. And the area over here is equal to 10 square meters. Right, those aren't very reasonable for a hydraulic system, but let's just say to make the numbers reasonable. Now, I'm going to say P1 equals P2. Right? P1 equals F1 over A1. That's going to equal, so I can find F1 is going to be P1, which is 100 newtons per square meter, times 1 square meter. That means that I put in a force of 100 newtons. If I have a pressure, if I'm applying a pressure of 100 newtons per square meter, that really means I'm applying 100 newtons over 1 square meter. Right, so that's the force that I've applied. Is my force for F2, is it going to be bigger or smaller than that, or equal? I'll try it again. Think hydraulic systems. I mean, what are hydraulic systems used for? What is the purpose of a hydraulic system? Like this case, this is a car lift, for example, where I want to lift a car up off of the ground. Right, I'll stop at 45, 45. Okay, very good. So C is the right answer. Because car lifts are meant to put in a small force and get out a what? A big force, right? I can lift a car just with a little bitty jack, just by moving my hand up and down with just, a few newtons of force. And I can lift this 1-ton car up off the ground. So C is the right answer. I'll show you mathematically how we can get that too. Now understand when you put B, you're probably thinking Pascal's principle, but B is not the right answer. The pressures are equal, but not the forces. And we exploit that fact. Now what we can do P2 here, P2 is 100 newtons per square meter. And so F2 then is going to be 100 newtons per square meter times 10, which is the area. And so you get a multiplicative factor of 10. So you get 1,000 newtons. I put in 100 newtons and I get 1,000 newtons. That's pretty cool, right? That you can increase your advantage by that much. All right, so that's Pascal's principle. Pascal's principle says that if you apply a pressure to an incompressible fluid, an incompressible fluid is just a fluid that cannot be compressed, which is all liquids basically. Then if I apply a pressure, then that pressure is felt all throughout the material, not only in the fluid, but also on the sides of the container. And this is used in hydraulic systems, for example, where I have a small input area and a large output area, and that increases my force and allows you to lift things like cars or whatever. Yeah? Yeah, Talia? Of course. Oh, no, it does make sense. The smaller the area, the more the pressure, right?
But that's not the same as this.
That's not the same as this. But it's not that, don't think about the area. I mean, you're right, the area is changing, but and this is true in the body too, by the way. Like when your heart contracts, it causes a pressure on the blood in your heart, but that's transferred all throughout your body. And that's what causes your blood to flow. Um, so, hmm. The liquid isn't flowing through these places. Like, we're just exploiting this by making this diameter of this cylinder bigger, but it's not actually flowing through this. Okay? Um, I can't think of a good way to explain it. It's not really the opposite. It's the same. But you're thinking of a flowing fluid. You're talking about something in the body. I don't know what you're talking about. What is it?
Like when you have hypertension or something, you're going to have more pressure
Mm-hmm.
because of the constriction.
Right.
So the smaller area you have that is flowing through.
Right. Yeah, if our pressure or if our area goes down, that means the pressure goes up. Right.
No, it's kind of the same thing. That's how I'm
Okay.
related because I don't know.
It's not the same though. You're thinking of fluid flow. Yeah, you're thinking of the flow of fluids, and we'll get into that, but it's different from this.
It's clearly very different.
It's clearly very different.
Very different.
Okay. All right, I'm gonna go down from here. Is that okay? All right, guys. Um, I want to just sort of set us up for the next thing, and then we'll talk about the different gauge pressures next time. All right, so imagine a tire, right? You have a tire here. My dad worked at a tire shop, so like I like all these tire analogies because I worked there. Like when I was 12, I started working there, sweeping the floors, and worked there as a teenager. So I have a tire, right? And I have pressure inside the tire. And a fully inflated tire is what, roughly? 40, 35, 30 to 40. I'm going to put 35. So 35 psi. All right? And I put my gauge on here. I have a little valve stem. And I can put my gauge on here. And it reads 35 psi. If you've ever checked the air in your tires. But what happens if that tire is flat? Right? The tire is flat. Yeah, the light comes on. Yeah, we just got a new car and it has one of those lights on it. It's really cool. All right. What does your gauge read now? What does it read? Okay, it reads less than 35, but what does it read? It reads 0. I mean, most gauges don't go down to 0, but if you were able to have a good gauge that read 0, it would read 0 psi. Okay? However, we know that there actually is air pressure inside this tire. What's that air pressure equal to? The atmospheric pressure. So I know that there is an actual air pressure inside the tire that's equal to 1 atmosphere, which is equal to, I don't know what it is in psi, but it's, 100,000 newtons per square meter. Okay? So in that, we're going to come up to 3 different pressures. It sort of illustrates that we have 3 different pressures when we're measuring pressures. And we'll talk about this next time. We're almost done. 3 different pressures. One is called gauge pressure. And this is just, like it implies, what the gauge reads. So that's just the pressure that the gauge says. The second of these is atmospheric pressure. And this is the pressure due to the atmosphere, which we've already talked about. This column of air that sits above your head. Oh, we're in class, Irvin. We're in class. We're still in class. That's okay. He's in my class too, but it's the next class. And then the next pressure is absolute pressure. All right, and absolute pressure is the sum of gauge and atmospheric pressure. So the sum of number 1 and number 2. We'll talk about these next time, but so for example, this pressure is which of these 3? This is my gauge pressure. And if I were to actually know the absolute pressure, it would be 1 atmosphere plus the 35 psi. So the absolute pressure here in this tire is more than 35. Y'all have a great day, okay? I'll see you Tuesday, and we'll have our reading quiz on through page, what page did I say? Through page 48 in the book.